Welcome. So in this set of video presentations, we're going to explore the mechanisms that make TCP, Transmission Control Protocol, a robust and reliable protocol for managing data transmission across networks. So we're going to explore different things. We're going to discuss a little on TCP windows and how sliding windows controls data flow, and how flow control mechanisms like the send window and congestion window ensure data is transmitted efficiently. We'll look a little bit at TCP slow start process and congestion control strategies, focusing on how TCP detects and manages congestion to maintain optimal performance. We'll look a little bit at some of the key topics like packet loss, duplicate acts, explicit congestion notification, the increased round trip timer, and things like that. This will highlight their impact on network performance. Now, all of this is kind of the tip of the iceberg, okay? But it'll give you, I think, a pretty good introduction into how all of these works. Because understanding these principles is really important for anybody working in the networking industry, as they are the foundation of reliable and efficient data delivery in modern communication systems. In these presentations, you're going to see that I include a lot of the text. So when you hear me talking here, you're going to see almost the exact text right on the presentation. I've done that so hopefully you can follow along a little bit more easily. You can even pause the video and kind of look at at what we're talking about and kind of hopefully just help you learn this a little easier. So let's get started. Okay, so we have PCA and PCB here. Okay, we're going to take a look at flow control. Flow control is a TCP mechanism that ensures the sender does not overwhelm the receiver with too much data. The sender regulates the rate of the data transmission based on the receiver's ability to process and buffer the incoming data. We'll see this happen. So in our data transmission, we have an IP packet, so that includes the IP header. We have TCP, so this plays an important role here. Here's the TCP header. And then we have the encapsulated data. Okay, we're going to be looking at something called the window, sometimes known as window size or known as the receive window or advertise window. This window is advertised to the sender in every TCP segment to inform the sender of the available buffer space at the receiver. We're going to see this here in a moment. Okay. So for example, when PCA, whenever it sends a segment to PCB, it might include for its window, says, don't send me more than 64,000 bytes. That's what would be here in the window field. Don't send me more than 64,000 kilobytes of data without first receiving an acknowledgement from me. We'll see that in a moment. It's also true for B. Every time B sends a segment, TCP segment, to PCA, it's going to include its window size. Don't send me more than 64,000 kilobytes of data without first receiving an acknowledgement from me. We'll talk more about this 64,000 kilobytes more in later videos. This is a very dynamic value. Now, the 64,000 bytes, this window size, this is the number of bytes that the sender can transmit before receiving a TCP acknowledgement from the receiver. What? We'll see what I mean in just a moment. So most modern operating systems typically set this to about 64,000 bytes. Let's do a little bit of an example here. So we got the network here in between PCA and PCB. This could be over a single LAN or it could be over many networks. Okay, so if PCB sends a segment to PCA, and in this segment, of course, it includes its window size. It says, don't send me more than 64,000 bytes of data without receiving an acknowledgement from me. That's what the 64,000 means here in the window size. Okay. PCA says, okay, I've got that. So this means that I'm not going to send you more than 64,000 bytes without receiving an acknowledgement from you. So I'm going to set I call it my send window to PCB. A is going to have a little send window that it says, okay, when I'm sending data to PCB, I have to stop after byte number 64,000. Okay, so my send window is set to the last byte that can be transmitted before receiving an acknowledgement from PCB. I have to stop at byte number 64,000. So let's start sending some bytes. Okay, so we can see in these TCP segments that we're sending 1,000 bytes for each TCP segment. And I've rounded it off to 1,000 bytes. We'll talk more about what that number most likely will look like in a little bit. Now, a few things to notice here. Notice that there's a TCP sequence number. That sequence number indicates the first byte of that segment. So this first segment, which is 1,000 bytes, would be sequence number 1, the first byte, to 1,000. The next one would be sequence number 1,000, the first byte in that segment, to byte 2,000, etc., all the way to the very last segment it's sending, sequence number 63,001, which is the first byte in that segment, to byte 64,000. Now, at this point, PCA says, oh, I've got to stop because my send window that you told me, your window size is 64,000, so I have to stop at byte 64,000. This is what is known as a stop and wait windowing protocol. Now, we're going to see a better way to do this here in a moment, okay? But the sender must stop and wait. In this case, PCA must stop and wait for an acknowledgement from PCB before continuing to send data. Now, assuming that all this data was received by PCB, we'll talk in later videos what happens if something's missing. PCB is going to send back an acknowledgement, okay? So in a TCP segment, it's going to include an acknowledgement number. This acknowledgement number is 64,001. This is called an expectational acknowledgement. The acknowledgement number indicates the next byte that this device expects to receive. So it received byte 64,000. That was the last byte PCA sent. So PCB says, great, I got the first 64,000 bytes. The next segment I expect from you should start with byte number 64,001. So now that PCA has received this acknowledgement from PCB, it says, okay, let me change my window side, my send window, not window, so I'm going to change my send window specifically to PCB. Might be sending other data to other devices that might have, we might be doing different things here, but specifically to PCB, I can continue to send data starting at byte 64,001, but I have to stop at, well, it's still the window size, which would still be included, by the way, in this this acknowledgement. Let's say it hasn't changed, it's still 64,000. So I will stop after another 64,000 bytes. I'll have to stop at byte number 128,000. So let me go ahead and start sending you those segments. So I'm going to send you the next segment, 64, that has the sequence number 64,001, the very first byte in that segment. Okay, so let's look at an improvement to this, something called sliding windows. Now, before we get started, let me explain what this here up here. Each one of these is showing 1,000 byte segment. Okay, so this is byte 1 to 1,000. This is byte 1,001 to 2,000, byte 2,001 to 3,000, 3,001 to 4,000. Excuse me. Each segment is 1,000 bytes. So TCP sliding windows. This is a flow control mechanism that can be dynamically adjusted the amount of data that the sender can transmit before needing to send an acknowledgement. What? We'll see what that means in just a moment. But we're going to see that this helps ensure efficient and reliable data transfer by preventing congestion and packet loss. It just kind of keeps things moving, keep things going, so we don't have to do a stop and wait. Let's take a look here. PCB once again says, my window size is 64,000 bytes. PCA says, okay, I won't send you more than 64,000 bytes without receiving acknowledgement from you. So my send window to you is going to stop at 64,000 bytes. That's where it's going to stop. Each one of these is 1,000 bytes. So let me start sending you some data. I'm going to send you 2 segments. Okay, I'm going to just keep on sending you segments. I can keep on going until I get to byte 64,000. Now, I've sent the first 2 segments, and meanwhile, PCB has received those segments. Now, this time, instead of waiting for all 64,000 bytes to arrive before sending an acknowledgement back, PCB is able to free up some buffer space, process these segments, and says, okay, I'm going to go ahead and send you an acknowledgement, letting you know I received those. Now, we can see that operating systems typically acknowledge every other segment. This is known as a delayed act. It means it's set after every 2 segments, it will go ahead and send an acknowledgement. Okay, so meanwhile, PCA now is receiving this acknowledgement. Okay, when it receives it, it says, oh, you've received the first 2 segments successfully. Now I know, because you keep on telling me, including in your acknowledgement, that your window size is 64,000 bytes. That hasn't changed. That can change. We'll take a look at that later. But for now, let's just assume that the window size does not change from PCB. PCA says, okay, you're telling me you received the first 2 segments so successfully, and your window size is 64,000 bytes. So now I'm going to adjust that over another 2,000 bytes. Okay, so I'm going to stop not at 64,000 bytes, but I can keep on going now to 66,000 bytes. Now, meanwhile, PCA, as it's receiving this acknowledgement, it's still sending segments. It didn't have to wait for this acknowledgement. So this can be happening the same time this is being sent. Okay, so these segments are possibly already, what we see, already in flight, but they haven't been acknowledged yet. So it has sent segments 3 and 4. Once again, PCB receives those 2 segments and sends back an acknowledgement saying, I've gotten those 2 segments. This acknowledgement 4001 means I've received everything up to byte 4001. Okay, up to, well, they restate that. I've received everything up to byte 4000. The next byte I expect to receive is 4001. Okay, well, PCA receives this and says, okay, now I've known you've gotten the first 4,000 bytes. You still have a receive window of 64,000. Let me slide this window over another 2,000 bytes. And again, meanwhile, it has been continuing to send these segments. So this is all happening kind of at the same time. While this acknowledgement is being sent, these segments are also being sent. Okay, and this continues. PCB receives these, says, great, I've received those 2. Let me send you an acknowledgement. Now I've gotten up to the first 6,000 bytes. The next byte I expect is 6001. And of course, when PCA receives this, it says, oh, okay, you've gotten up to byte 6,000. I can slide that window over because I know those 6,000 bytes, hey, they're taken care of. Okay, you got them, everything's good, nothing has to be resent. And I can continue to send you up to byte 70,000. Okay, now we're going to explore more in later videos here in a moment. But before we get there, I want to talk a little bit about how much data is actually being sent. We've been using 1,000. That's a nice round number. Okay, this is called the TCP maximum segment size, MSS. This is the largest amount of data in bytes that a device is willing to send or receive in a single segment. How's it come up with that? Okay, we're going to see here in a moment, but this number is typically 1,460 bytes for IPv4 packets or 1,440 bytes for IPv6 packets. Okay, how did it get that? Well, the standard Ethernet maximum transmission unit for the amount of data that can be put in an Ethernet frame is 1,500 bytes. Okay, let's take a look at that a little bit more closely. Okay, so how do we get 1460 bytes for IPv4 and 1440 bytes for IPv6 packets? Well, if we look at the IP header, an IPv4 header without any options is 20 bytes. An IPv6 header is fixed always at 40 bytes. TCP header is 20 bytes. So that leaves us to get to 1,500 bytes here for the Ethernet MTU. That would leave us with, well, for IPv4, 1460 bytes of data or 1440 bytes for IPv6. So this is typically the number that we're going to be seeing instead of 1,000. And we'll use that in later videos. So what are those later videos? Well, here we go. The next video is going to be on flow control. We're going to take a look at the send window and congestion window. All right, hope to see you there.